May 2021. My name is Samara from ITS Global Engagement and will be your Master of Ceremony this afternoon. Thank you for joining our guest lecture series on SDGs today. Before we start our agenda, let me inform you of some rules for the event. First, please fill your attendance at bit.ly/attendance_GLS SDGs. Our committee will also send the attendance link in the Zoom chat room. For participants who wish to get an e-certificate and stamp for it, please fill the attendance 15 minutes after the session starts. Second, participants who wish to ask questions during the question and answer session, please send your question to intip.in/Q&A/GLS SDGs. The link for questions will be listed in the Zoom chat room as well. Or you can ask directly by clicking the raise hand feature. Ladies and gentlemen, today's guest lecture series on SDGs topic is Passive Optical Access Network and its recent development, and Photonics and Fiber for their use in medical physics and biophysics, that will be delivered by our speaker, Associate Professor Nadiatul Huda Zulkifli from University of Technology Malaysia and Professor Dr. Agus Rubianto from Research Center of Fundamental Science ITS. The lecture will be moderated by Dr. Nasori from Research Center of Fundamental Science ITS. Before we start our agenda, allow me to deliver our schedule today as follows. First is the opening, followed by introduction to moderator and speakers, and then we will proceed to the lecture session, followed by Q&A session. Next, we will proceed to the certificate awarding, and last but not least is the closing. Now, before we proceed to the next agenda, allow me to introduce our moderator today. Our moderator today is Dr. Nasori from Research Center of Science Fundamental ITS. He received his education at TU Ilmenau, Germany, and Master at ITS Surabaya and Bachelor at Unhalu RUAT. His research interest is functional 3D nanostructure for various applications, and he has some research collaboration at TU Ilmenau and Zhejiang University. Now, without further ado, let us proceed to the main agenda. To Dr. Nasori, the time is yours. I'm sorry, Doctor, I think you are still muted.
We cannot hear you, Dr. Nasori. You are still mute your Zoom. Yeah, sure, Dr. Nasori. Wait a minute.
Okay, thank you very much. Okay, MC, thank you very much for a nice introduction. Ladies and gentlemen, good afternoon. Thank you very much for coming for this GLS guest lecture series. For as stated in the announcement, the seminar on this occasion will discuss about passive optical network and its recent development, and photonic and fiber for the use in medical physics and biophysics. For this, of course, really need information as well as an effort to equalize perception as well. All hope in internal seminar this time. Before presenting the material, I will give a little introduction related to the material that will be delivered by presenter. Basically, scientific forum like this is very important and interesting for us to follow, because there is a lot of important information conveyed by present that we usually get. However, in general, the delivery of this information will be easier to understand if the discussion is carried out effectively. Therefore, it is hoped that all of us can pay attention to and follow this discussion as well as possible. Okay, before the first speaker deliver the material, I will convey some of the prevision of core event. The first one, we give speaker time to deliver the material as well as discussion for around 40 minutes. As long the speaker deliver the material, there are no interruption. After presenter deliver the material, a question and answer session will be opened. You can directly raise your hand, and also you can chat in you can write it in chat Zoom. Thus the rule that we will use. Furthermore, we immediately invite the speaker, but I will mention for you about the CV from first speaker today, Associate Professor Nadiatul Binti Zulkifli. Yeah. He come from Malaysia, from Department of Communication Engineering, Faculty of Electrical Engineering, University Technology Malaysia. Professor Nadiatul Huda, you are present here? Hello?
Hello, Assalamualaikum, Dr. Nasri. Yes, I'm here.
Okay, you sounds very good.
Okay, that's
You
good.
have a professor membership from graduate member from Lembaga Juruterra Malaysia, member of Institution of Electric Engineer, and then member of Optical Society of America, member of E3 Photonic Society, and also certified for fiber optic technology. You have academic qualification from University of Sussex for PhD Electrical System Engineering, right? 2019, right? Okay.
University of Essex, sorry.
Oh, University of Essex. And then the same University of Essex for Master Science in this Computer and Information Network, and Bachelor from Electrical Communication Engineering, University of Technology Malaysia. Okay. For administrative experience, you have a lot experience actually from 2010 till now. You have a lot administrative experience, and also you have supervision as a main supervisor or co-supervisor from 2012 till now. I think you have more than 12, yeah. And also you have a master by course and research. And this one is most important thing. You have H index around 9 with Scopus, with a journal more than 12. Actually, I think it's more than right now. And Scopus index you have more than 18 exactly. And not index maybe this one in local, yeah, local publisher, yeah, too. And you have a lot conference. You have a lot conference, and you have also mentioned here original book. You have write down, and you have also write as a book chapter here. I think it's very amazing curriculum vitae from you, Professor Zulkifli. I call you Professor Nadia Huda or Zulkifli or something like that.
You can call me Nadia.
Nadia, okay.
Nadia, yeah.
Okay. The first time you have around 40 minutes, and we time right now is yours. Okay, you can direct go to the your presenters. Prof. Nadia, you hear me?
Okay, can you hear me? Sorry.
Yeah, sure.
Okay. What about the slide?
Yeah,
Okay now.
clear, yeah.
Sorry. Um. Okay, let me continue. Topic for today's presentation is passive optical networks and its recent development. Okay, first, allow me to just introduce briefly my university, University Technology Malaysia. We have two campuses in Kuala Lumpur and Johor Bahru. Okay, so these are where we are located. And this is our main campus in Johor Bahru. Yeah. Okay, so this is the center of our university, the mosque, and the rest are administrative buildings and also the faculties. Okay, so this is also where I am from, my faculty. And another campus is UTM campus Kuala Lumpur. Okay, this one is located at the center of Kuala Lumpur. And some facts and figures of UTM. It was established in 1972 and its status now is a research university. So it started with teaching university, of course, but then the emphasis shifted towards more emphasis on research. So we can see from the number of postgraduate research students that are quite approaching the undergraduate students. And we have also quite significant number of international students, yeah, to expose our staff and students to the global culture. And these are the faculties in UTM. Okay, we have 7 faculties, and one of the biggest engineering faculty in Malaysia is in UTM. And under here we have a number of engineering schools. I'm from the School of Electrical Engineering, Division of Communication Engineering. Okay, research-wise, I'm with the LCRG research group, okay, which focuses on optical-based research. So we have the research areas, not only in network and communication, but also devices and also optical sensors. Okay, so now I'll continue with contents that are related to my talk. Today, we are in the age of Industry 4.0. And in this age, the innovations basically are data driven. Okay, where we have many sensors that send data to the servers. And this requires very high speed and also reliable telecommunication infrastructure. One of such innovations is smart car. Okay, so smart car has vast amount of sensors, enormous data transmission that need to be handled and analyzed. And the communication has to be very fast, yeah, almost instantly, because in order to avoid catastrophic events such as accidents and death. Okay, so this is also the main aim of smart car, which is to avoid carelessness and mistakes from human. So it has to be very responsive. Okay, And to support Industry 4.0, networks have to be not only have high capacity, also need to be very mobile. So it has to be ideally it needs to have both superior wireless and also wired networks. Okay, so the increased capacity of later wireless network generations such as 4G and now 5G comes at the expense of decreasing cell coverage. When we move to more latest wireless network generation, we get higher bandwidth, but the cell coverage will be less. That's why we need many antennas. And as for wired networks, it offers more reliable connection, and the wired networks and specifically the optical network serve as the backbone to the wireless networks. So this figure shows a typical 5G architecture that is by Vive Solutions, which is a telco provider. You can see from the next generation core to the antenna, the 5G antenna systems, we have fiber link. Okay, so all connections between these two ends are by fiber links. So optical fiber technology is the key to today's high-speed and long-distance communication infrastructure. So the basic rule is that if you want to transmit more than 10 megabit per second data over 1 kilometer distance, fiber is the preferred medium. Okay, what is optical fiber communication? I'll start from the very basic because so that can cover the background of our audience that is quite broad. Okay, that was what was informed by me. We have quite broad audience background. Okay, so what is unique with optical fiber communication is that information is carried in the form of light inside optical fiber that is made of silica or polymer. So normally we have data from users in form of electronics, and then this data will be converted to optics, okay, modulated, and then becomes in the form of light. So and then it will be transmitted over fiber optic cable, and this light will be detected by receiver and converted to electrical back. So if we look at the cross section of fiber optic cable, we have core, the very basic cross section. We have core and surrounded by cladding, coating, and also buffer. Light travels basically confined inside the core. And for the largely used transmission fiber, which is single mode fiber, the fiber core is just around 10 micrometer. Okay, if you compare it with the diameter of our hair's diameter is around 70 micrometer. So ours is like 7 times less. Okay, the core, fiber core size. Okay, why optical networks? So what I've already informed that optical fiber technology is the key enabler that revolutionized the whole communication world. And optical networks basically is data communication networks that is built using optical fiber technology. Okay, and it basically for optical networks, we have many interconnected fiber links that comes from different nodes or exchanges. Okay. If we compare fiber with the legacy copper, for instance, such as ADSL that use copper, apart from the huge capacity provided by fiber over long distance, fiber is also more immune to electromagnetic interference and more resistant to chemical and environmental effects. Okay, and since the data that is delivered to users through fiber optic and some optical components without electronics and power supply, then the maintenance will be less. Okay, since we don't we don't need to power so much compared to copper, and it has longer lifespan, more than 25 years. And also, since it's made of silica or polymer, then it's the raw material to produce fiber is also cheap and abundant. Okay, this is compared to copper. So that's why copper, we have problem, because of its quite high value. Then we have a problem of people stealing copper from all these cables. Okay, next, let's look at one type of optical network, which is fiber to the X. Okay, so in our telecommunication network infrastructure architecture, we have these three domains from core, metro, and access. So FTTX is used within the local loop. So this is the last segment to the provider's network that connects the end user to the carrier network. So it provides internet connection to household, companies, and organizations. Okay, this is because when technology matures and components, devices can be produced massively, the component and system costs reduce. Okay, so now we can afford to bring optical network closer to the public. So FTTX is an abbreviation for fiber to the X, where this X represents a basic name or entity such as home or node, can be C cabinet, okay, building. So when fiber enters a living or working space, is referred to FTTH. So it connects central office to the homes. So signal, then after that, in homes or building, the signals can be transmitted across the space using methods like twisted pair, coaxial cable, Wi-Fi, or additional optical fiber for indoor inside building. Okay, so FTTX is now experiencing rapid growth all around the world, and including Malaysia, because there is a huge demand for high-speed triple play services, where you have one connection for three main services: internet, video, and telephone. Okay. Okay, let's look at the benefits of FTTH. Okay, FTTH is very appealing because the main infrastructure is future-proof. Yeah, so it means that it can meet the broadband demands in the future. And fiber optic, like I said, it has almost limitless capacity and can transmit over long distance. Homeowners can also benefit from the faster broadband and improved bandwidth. We can stream high quality video, and we can also connect many devices simultaneously. Okay, the whole house can be connected over the same the service that we subscribe. Okay, so obviously this is a more economic solution, for the customers, because we got a cheaper price and with better service quality. From my experience, before I use FTTH in my house, so I had to subscribe to different companies for these three services. Okay, television using satellite TV provided by Astro, and telephone internet using copper provided by TM. And imagine the speed is just 1 megabit per second. But when I subscribe to FTTH using, I subscribe to the product is called Unify by Telecom Malaysia. So at 100 megabit per second, the price is cheaper than when I combine the cost of these two. So I got connected. I can use all these three services at the same time. which is it's very good, yeah, for the customers. Okay, let's look how FTTH is implemented. So the implementation of FTTH can be categorized into two: device-based and also topology-based. Okay, for device-based, it's either we use passive or active device. Okay, so for the first one, passive optical network or PON, passive optical splitter is used to distribute signals, and there's no power supply to power up our passive optical splitter. And for the second one, active optical network, it uses electronic Ethernet node as aggregator because it's an electronic device, so it needs power supply. Okay, as for topology based, we have two types, which is point-to-point and point-to-multipoint. So for normal users, we cannot afford point-to-point, yeah, because it uses a dedicated direct fiber link from network edge to the customer. So normally this can be subscribed by big enterprises, and normally they subscribe to premium service at very high data rate. For point-to-multipoint, this is on a sharing basis where many users share the cost of infra, so it brings the cost down. It's more economic. Okay, and we can use either active or passive devices to distribute signals. Okay, so considering all these methods, the most widely adopted is passive optical network based on point-to-multipoint topology. Okay, so this is the most widely used around the world because of its more economic. Okay, so now let's look into the details of passive optical networks, point-to-multipoint. Okay, both PON and AON, active optical network, use fiber optic to link between the center to the home users. But the main distinction is the optical passive splitter over here. Okay, so this is unpowered system. Okay, they transmit splits the power from here to the many users at the ONUs. So signal distribution to many users done without need for electrical supply. Okay, here we have our from OLT to this ONUs is optical distribution network, and our LT is connected to the core network through network interface, and connected to passive filter through feeder fiber. And after splitter, we use distribution fibers to link between passive splitter and the ONUs. Okay, and if we look at the potential applications of PON, can be used the different various customer segments from home, like single unit, house unit, or apartments, building, work, offices, and also wireless cells. So for the very basic PON, the one that is deployed right now is known as gigabit PON. There are three wavelengths. Okay, from OLT to ONU is known as downstream. Okay, the downstream wavelength is 4090 nanometer, and we also reserve for RF radio video broadcast at 1550 nanometer. Upstream from ONU to OLT is done at wavelength 1310 nanometer. Okay, in terms of multiplexing, it adopts TDM, time division multiplexing. So it enables various end devices to send and receive separate signals through common fiber infrastructure. So from OLT, these TDM signals will be broadcasted to all ONUs. And this is downstream. For upstream, okay, we use TDMA, time division multiple access, where time slots are reserved for these ONUs to send data in turn. So they have to abide to the rules to avoid collision, yeah, along the fiber link. Okay, as for the point to multi-point topologies, there are a number of topologies that can be adopted. Yeah, the star topology, where we have all the ONUs connected to one central, and bus topology, also ring topology, and tree topologies. So these are the possible topologies. Yeah. Okay, the variation of ponds. So around the world, there are two major PON standards, gigabit PON and Ethernet PON. So both are accepted as international standards. They have basically they follow the same network topology methods, the FTTX applications, incorporate the same WDM technology, deliver the same wavelength both upstream and downstream, and also for the RF video, the same wavelength bands. But there are distinctions between these two in terms of protocol wise. Yeah, EPON, Ethernet PON. So this was introduced earlier. Yeah. So the aim of EPON is to have a simple system beginning using existing Ethernet devices without making so much changes. And EPON has strong dominance in the East Asian countries such as Japan, Korea, China. Okay, the first taker was NTT from Japan. So the IEEE 802.3 standard was ratified ideally to carry best effort Ethernet traffic. So, okay, it uses symmetric 1 gigabit per second downstream upstream at splitting ratio 1:16. But because it's best effort, not supported, so in terms of security and QoS. Okay, as for GPON, which is proposed by ITU, International Telecommunication Union. So ITU wanted something that is more, a solution that is more efficient and aligned with network development that provides full service access networks. So it carried packetized traffic, borrowing from synchronous high-speed networks such as SDH, SONET, and it uses similar generic framing procedure known as GEM. Okay, so for GPON, it's known as GPON encapsulation method. Okay, so traffic, including Ethernet, will be encapsulated in GEM and increase transmission bit rate to, if you compare downstream 2.5 and upstream 1.25. Splitting ratio is also higher, 1:64. And security, because it's more superior in accepting new ideas, new services. So the QoS and security functionalities are offered in GPON compared to EPON. Okay, for current GPON deployment, okay, it's based on TDM. Many ONUs share the bandwidth. The frame is 125 microsecond. So any ONUs has to be labeled for identification purpose so that ONU knows which OLT knows which ONUs are sending or data. It has a hierarchy of labels to differentiate or identify ONUs, TCONs, the VPs, VCs, and also the port ICs. So it supports two modes, the previous protocol, which is ATM, and also its own protocol, which is GEM. Okay, so this figure shows the frame structure of GPON, the downstream and below upstream. So it supports a 125 microsecond long frame, which is compatible with the legacy digitized TDM. So the downstream is broadcasted to every ONU, and ONU use the information in the this one physical control block downstream to extract its own data. So if there's no data to be transmitted, downstream frame will still be transmitted continuously and utilized for time synchronization. So as for the upstream, it contains multiple transmission bursts from ONUs. So along with payload, okay, this stream burst also consists of allocation ID, and the rest are control information and also data information. So when traffic reaches the OLT, ONU traffic will be queued based on QoS, depending on the types of TCONs. Okay, GPON has 5 types of TCONs to provide QoS in the upstream direction. Okay, so these are the 5 TCONs and the QoS and that are supposed to be supported. So the highest priority is TCON 1, is time sensitive fixed bandwidth. TCON 2 has higher delay than TCON 1 and assured bandwidth. TCON 3 no delay guaranteed and for assured and non-assured bandwidth. For TCON 4, it supports best effort services such as Ethernet. And finally, 5, it can be mix of all these traffic types and it's for general traffic flow. Okay. So I just want to show you the how the real equipments look like. Okay, so this is equipments in the setup of laboratory. So this is fiber spool. Below the spool, we have the OLT equipment, and it's connected to this passive splitter. Okay, and then from the splitter, one branch is connected to this ONU. Okay, and then this is how these equipments and fibers look like at our homes. And so this is my home. Okay, so this is the indoor fiber that is connected from the fiber distribution box, because it's there's a fiber distribution box along the road, and then from splitter there, fiber will be sent to here to ONU, and then from ONU I connect to wireless access points, and then instead of apart from wireless access point, we can also connect to many other services like TVs, telephones, etc. Okay, so let's look at the PON progression. Basically, we can categorize into 3 generations. So first generation is the one that is deployed commercially. Yeah, this one for GPON and EPON. Okay, this one I've already explained before. And for the next second generation, you can see that it increases the transmission bit rate. Okay, for up to 10 gigabit per second downstream. Okay, for EPON, 10 gig EPON, it provides symmetric downstream upstream. But for GPON, we have 2 classes. GPON 1 that is asymmetric, and GPON 2, which is symmetric. Okay, so symmetric here refers to the similar rates for downstream and upstream. And then for the third generation and GPON 2, okay, further increased the data rate up to 40 gigabit per second. Okay, so basically all the technologies and solutions for these 3 generations have already been agreed in a consensus by ITUT. And as for NGPON 3, it's not finalized yet, but we have a number of candidates that are promising. Okay, and each generation has its own wavelength band, yes, so that to ensure coexistence. Okay, so let's look at comparison between NGPON 1 and NGPON 2. So NGPON 1 is based on the same as DPON, based on TDM PON. Okay, it's just that it increases to a higher rate. Yeah, so because of the higher rates and new wavelength band, so we need new set of LLT and ONU modules. And the splitting ratio also same, the maximum reach same. But if you want to coexist with GPON, we need WDM filter. As for NGPON2, there are many candidates for NGPON2, yeah, which is can be based on TDM, WDM, OFDM, OCDM, okay, many candidates. But after long discussion and study, so TWDM PON is the one that is chosen as the best candidate because of less disruption to the existing infrastructure, and it's also most economic. Okay, so data rates are higher, 40 and 10. Wavelength band also is different. Splitting ratio and much higher. The maximum 12256, and reach also up to maximum 100 kilometer. And apart from new OLT and WM filter, if coexist, it also requires AWG filter to demark or marks the stack wavelength, and colorless ONU. Yeah, so the transmitter and receiver at the ONU have to be tunable. Okay, so the basic structure of this TWDM PON is based on 4 stack of XD.1. If you see, we use 4 stack of XD.1 at different wavelengths. Then this wavelengths, okay, basically it's kind of, that's why it's much more compatible, right, with the existing GPON. And this is the architecture of NGPON2 access network. Okay, so we have 4 transmitter here. Okay, so each ONUs will receive its own wavelength and also transmit back upstream at its own wavelength. So we have multiplexer and demultiplexer, yeah, to separate, differentiate with all these wavelengths that come from different ONU. Okay, so what's next? So we have looked at the 3 generations from GPON, NGPON1, and NGPON2. So the next more logical idea is to utilize fully the existing the existing technologies that we have. So the first idea, what's next, is to coexistence of these different PON generations to fulfill bandwidth demands from different customer segments. GPON, for example, targeting residential subscribers, and GPON1 business enterprise. And for services that require more stringent requirements, like more sensitive to delay, higher capacity, can give NGPON2. So this is the example architecture when if we coexist NGPON2 with the previous generations. Okay, so OLT GPON represent the first generation, and then XGPON the second generation, OLT TWDM PON, this one the third generation, which is NGPON2. Okay, so this is how they coexist. They use the same fiber, but we need at the transmitter as OLT and ONU, we need to demultiplex or differentiate wavelengths according to their generations. Okay, and also what's next, utilizing the existing equipment, is to have go for longer reach PON. Okay, for longer reach PON, it's very attractive because by increasing the distance, we can reduce the number of CO, central office or LT nodes. We use less equipment, and it's also eliminate the metro ring backhaul. Yeah? So we have direct access from this access network, from user to the optical backbone. So in order to compensate for the longer fiber distance, we use remote extender, which is optical amplifier. So in the research, people have already carried out demonstrations, experiments using a number of different amplifiers such as EDFA, erbium doped fiber amplifier, Raman amplifier, or semiconductor optical amplifier. Okay, as for NG-PON3, NG-PON3, this not been finalized yet. Yeah. So it supports higher data rates at 100 gigabit per second downstream and 40 gigabit per second upstream at least, and the minimum. Currently, there are 3 strong new potential technologies that have been identified for longer term NG-PON3 that is capable to transmit up to terabit per second. Okay, why I say longer term? This is because the GPON that we use right now is already fully established. Okay, the market for GPON is also quite large. And the NG-PON 1 and NG-PON 2 are also still new to the market. Okay, so it takes quite many years for NG-PON 3 to be commercialized. Okay. So there are 3 candidates: WDM-PON, OFDM-PON, and coherent PON. Okay, so OFDM and coherent are solution that's already, it's not really new. We have they're already very established and mature in the other types of networks such as wireless networks. Yeah. WDM-PON is, and the concept of WDM-PON is that each ONU gets its own wavelength. Okay. So like TDM-PON, they have to share, and they use the one wavelength but share, right? But for WDM-PON, each has its own wavelength, and so each ONU can receive peak rate of that particular wavelength. Okay, and it has been widely researched since 1990s. But the drawbacks is more costly. Okay, because we need to use AW and DMUX to replace on top of our optical splitters, and since we need, ONU has its own wavelength, we also need many lasers, yeah, to get dedicated for these wavelengths. So one solution that is already being demonstrated, yeah, by in the commercially is not commercially but by a telco company is self-seeded WDM-PON. So using another device such as RSOA, yeah, the RSOA provide the light source to ONU instead of ONU use its own laser. So it carries this source to the ONU, so that ONU can modulate this light source to be transmitted at upstream. Okay, so for OFDM-PON, data to each ONU is transported using different subcarriers and time slot. It's very attractive because of the high capacity given the excellent bandwidth granularity. But the downside is that the cost again, yeah, because it uses high speed DSP processor. For coherent PON, okay, coherent PON is also has already been used for the later network generations, yeah, wireless network generation, especially it uses advanced modulation formats that based on coherent transmission. So such as 100 gigabit, 100 gig QPSK. So it carries the same concept, exploit and apply it in optics. So it's very spectrally efficient. So we can use and we can make use of our spectrum much better. And it also offers huge network capacity, but again is most costly because of the high speed and the SP processor electronics that we have to use at the transmitter and the receiver. Okay, so our research works in PON. What have we done in PON? So there are a number of areas that we look into, such as physical layer and GPON2, looking at the advanced modulation formats and different techniques to boost the reach and also the capacity, and DBA in GPON and SGPON. So such as the more power efficient DBA. DBA is dynamic bandwidth allocation. This is when ONU wants to transmit signals upstream. Yeah. So if we make the bandwidth allocation more dynamic, then we can allow maybe there's certain instances that a specific ONU do not plan to transmit signal, so the extra bandwidth can be used by other ONU. So that's why I call it dynamic. So depending on a number of situation. So we have students working in green DBA, more power efficient DBA, security aware DBA, and long reach DBA, and fault monitoring in GPON. So monitoring in Japan is also quite an issue because of the passivity of our PON. So it's difficult to monitor if there are faults that happen at the along the link, especially after the splitter. Okay, so we have a project where we use a sensor, optical sensor, based on fiber Bragg rating to detect the fault, and also machine learning to predict the faults based on the data and that we got from experimental testbed and also simulation. And then students also work in integrated wireless PON area, looking at power consumption of this network architecture, green routing algorithms, and quality of service. These are the references that I used in my presentation, where from 11 to 24 onwards, publications by our students and staff. Okay, so before I end my presentation, so we started by saying the importance of having high speed and reliable telecommunication infrastructure to drive innovations as to support our industry 4.0. But due to this pandemic, COVID-19, it has become a basic need to fulfill our very fundamental human functions, such as studying, meeting our family members, and buying groceries. Okay, so we're very thankful that these technologies like video conferencing, like this, the one that we are using at the moment, are available now during COVID pandemic, and we honestly we should ask ourselves whether can we survive without these online services. Okay, so with that I end my talk, and thank you very much for listening. So I'm not so sure whether I'm ahead or or not in terms of time. Okay, so I pass the floor back to the moderator.
Okay, thank you very much, Mom. Okay. You have a nice talk and how economic it is. However, still has a lot of challenge and high technology for installing this fiber. However, in daring era, like COVID era like this. A big applause, guys, for Professor Nadia.
Thank you very much.
Before arriving at the question and answer session, we invite Professor Agus Rubianto. Are you hear me?
Yes, yes. Okay, very clear.
Professor Agus Rubianto, I'm to deliver the second session for this afternoon. Before I introduce Professor Agus Rubianto, the education from Paderborn University, Germany, from Dr. Renat, and Magister Engineering and Science from Indonesian University, and also Bachelor of Science from Institut Teknologi Surabaya. As professional career, he got Indonesian Associate Basic in Medicine and also Indonesian Basic Society. He has a lot of career in academic and non-academic. As now he has a chair of Information and Communication Technology cluster, API, and also head of Fundamental Science Research Center, ITS. Before he sit in as Dean of Faculty of Science, ITS 2017 till 2019. Now he professor in basic, yeah, professor actually from medical physics and biophysics. Professor Agus Rubianto, are you ready for your presentation?
Yes, sure.
Okay, you can going to share your presentation, please.
Yeah.
And
Okay. Let me to share my list. Okay. Okay. Thank you, Dr. Nasori, for the nice introduction. Yeah, dear Professor Naria, apa kabar, Prof?
Alhamdulillah sehat, Prof.
Ya,
Terima kasih.
dear participant, Assalamualaikum warahmatullahi wabarakatuh. Good afternoon. It is great pleasure to me as speaker in the guest lecture series on Sustainable Development Goals, with organized by Directorate of Global Partnership. My lecture topic is today is photonic and fiber optic, their use in medical and biophysics. Yeah. The outline of my topic is introduction, photonic integrated circuits, fiber optic sensor, application, and medical and biophysics, and a conclusion. Before that, I would like to introduce ITS. Yeah. ITS is a leading university in the field of science and technology in Indonesia. In 2019, it was ranking the fourth best university in Indonesia and was declared as the best autonomous university, rank 1, yeah, in the implementation of program activities and budgets. And ITS also received the Vidyapati Award, rank 3, as an innovation university, the Sinta rank 3, yeah, for the highest number of publications. And the international level, ITS was ranked in the third best university in Indonesia, according to the Time Higher Education World University rank in 2019 and 2020. Moreover, ITS was ranked 200, yeah, 1 plus, yeah. Plays a central role in our life on the most fundamental level through photosynthesis. Light is the origin of life itself. Yeah, the study of light has led to promising alternative energy source, life-saving medical advances in diagnostic technology and treatment, like speed internet, according to Professor Nuria, and many others discovery that revolutionized society and shape our understanding in the universe. This technology were developed through century, yeah, by fundamental, by Ibnu al-Haytham with Kitab al-Manasir, Book of Optic, in 1015, including Albert Einstein, yeah, work in the beginning in the 20th century when the foundation of the photon theory of light, and also the first laser successfully operated by Theodor Neumann in 60 May 1960. The International Day of Light is celebrate the role lights play in the science, culture, and the art, education, and sustainable development. And in the field as diverse as in medicine, communication, and the energy. The celebration will allow many different sectors of society worldwide to participate in the activities that demonstrate how science, technology, art, and the culture can help achieve the goal of UNESCO building the foundation for peaceful society. The International Day of Light is celebrated on 16 May each year, the anniversary of first successful operation of the laser in 90 by physics and engineering Theodor Neumann. The first laser is named Laser Ruby. Light is life. Without life on our planet would not exist. In studying light through astrophysics, we delve into some of the deepest mysteries of the universe. In exploring optics, quantum optics, we plunge into the heart of matter itself. Light-based technology are essentials in the healthcare, where optical instruments and tools are used for analysis and imaging, and ultraviolet light source are used for sterilization in this area, in ultraviolet sterilization. This technology are also essential for sequencing genomes, like that of the SARS-CoV-2 virus currently wreaking havoc around the world. Photonic integrated circuit, or we call PIC, or we can say also integrated optical IOC, have been developed to replace electrical integration circuit or conventional optical signal processing system, composed of relatively large discrete element. The major advantage of the PIC are increased bandwidth, expanded frequency wavelength demultiplexer, low-cost coupler, including bus accept types, expanded multiple switching number of pole switching speeds, like Professor Nadia said, and also small side with lower power consumption, bad fabrication economic, improve reliability, improve optical alignment, humidity to vibration, and also from the electromagnetic. But the major disadvantage is high cost development, new fabrication technology. The main structure of integrated photonic integrated circuit is waveguide, which is used to guide, to manipulate light signal. The operation of waveguide is based on the total reflection. So that means the light is propagated in the material with the higher refractive index, and the surrounding is lower. In the high refractive index, allow the total internal reflection in the core and interface. And the waveguide dimension refractive index contrast between material and the used wavelength determine if they are only multiple or single mode. You can see here in the picture, there are two types. It's a single mode, it's with distribution Gaussian like this, and all multi-mode. The basic component of PIC divided by two. Passive component like waveguide, coupler, switch, optical interconnection, and also filter, add drop filter, multiplexer, dispenser, compensator, attenuator, and gain equalizer, isolator. And also the active component is like erbium doped fiber amplifier, optical, laser, light emitting diode, optical modulator, optical detector, and also optical wavelength converter. But we can also declassify it, yeah, based on the integration. Somehow is a monolithic integration. That means every component is in one substrate. And the second is the hybrid integration between one block with the other block, and also with modular integration that we can puzzle, yeah, one from one modular with the other modular. And also based on the substrate material, normally use indium phosphate, gallium arsenide, lithium niobate, silicon, and silicon on silica, silicon and insulator. Let's see, here is like electro-optic integration, yeah, in one chip. Yeah, that means there are passive waveguide and thermal pass shifter here. And also we can integrate it with polarization and splitter rotator. So we can also the splitting by integrating coupler, and also from the ring resonator. Yeah. How to fabricate it? Yeah, we have a strategy. Yeah, whether we use indium phosphate or we use the other material. So we can think in our mind, we fabricated the active function like semiconductor, optical, amplifier, or photodetector, or we combine between passive function and also with the active function. So we look here like in the picture, we can combine between the passive component and also the active component. The laser is embedded, yeah, in the one substrate. So in the substrate, normally we can use indium phosphate. The material substrate is also lithium niobate. Yeah, have excellent properties in the electro-optical and acousto-optical, photoelastic, photoreactive, and nonlinear optic. That means if we can modulate it, we can use these properties to develop integrated optic or photonic integrated circuit. Yeah, and the basic technology is a thin film technology. So there are several steps to fabricate it. Yeah, the first, normally we use a thin film technology by evaporation. For example, we use metal from titanium, erbium, and ferrum. Normally, ferrum use DFB, and also reflector like gold and silver, AU, aurum, and also from the electrode. However, we can use also thin film from the end of the chip, optical chip. Yeah, we use as insulation or anti-reflecting coating by silicon oxide and titanium oxide. How to define the integrated circuit? We use microlithography and with positive etching. Normally we use for optical waveguide, and negative resist is from electrode. Yeah, and also the next step is by diffusion. For the active component, we normally use erbium, and the grating with the ferrum, and also from the acoustical and optical waveguide is titanium. And before we go to the market, of course, the last is assembling and pigtiling. We need optical coupling, and not only optical, but also the electrical coupling and with the packaging. So here is one of the example of optical waveguide. Yeah, we fabricated normally with erbium evaporation for the active component. Yeah, if we want to develop laser and titanium, erbium, lithium niobate, there is one this step. Yeah, from erbium in diffusion, and also we fabricated with titanium in diffusion with stripe waveguide. Yeah, on the top of substrate and erbium. Yeah, how to define the integrated circuit? Yeah, we should design. Normally, we use software. There are many software in the world that can be developed. As I develop integrated circuit, I use Tor software that can, for example, we should define how to, for example, here there are three components. Yeah, one is the optical waveguide, the second is acousto-optical waveguide, the third is electrode transducers together. So that's mean we should define step by step, and also there are three masking in this condition. I would like to explain how fabrication from the substrate until packaging devices, and we can use in the industry. For example, here I give example about the lithium niobate wafer. Before we define with photolithography, the lithium niobate is showing with the special size. Normally is 2 centimeter times 20. That's depend on the using, and it's showing, and we can define with metal evaporation by maybe titanium, or erbium. That depend on what we want to develop, and photolithography to define the structure of photonic integrated circuit and the diffusion. And also we analyze this. If there are good, we can through with the polishing, and we can make anti-reflection coating with silicon oxide, and also we can maybe somehow with transducer and electrode, we can use with lead-off processes, and the last we can pick tiling with fiber optic. And so here is one example for the characterization of every component. Normally we as laser and light source came into in the chip, and also through in the optical waveguide. For example, here is acousto-optical component. They can convert the light polarized light. For example, if they come into STM, they can convert to TE, and vice versa. And they is combination between optical and also surface acoustic wave. Is the mode converter is a function of frequency. So we can see like this, and also we can develop all the electro-optic mode converter is we use index reflective of electro-optic in the substrate and lithium niobate, and also we can combine between mode converter and phase shifter together. And the last we can grip as a mirror with RU, with the gold. So after fabrication, normally we pick tiling by laser. For example, like this, here is one of the packaging, PIC, integrated acousto-optical heterodyne interferometer that can use for laser vibrometer. Nah, yes, I would like to explain about the fiber optic. The fiber optic sensor is also the excellent candidate monitoring for medical, and also from biophysics. So they have many advantages. It's easy integration into wide variety of structure, and also including composite material with little interference due to their small size. And also inability to conduct electric current, immune to electromagnetic interference and radio frequency, lightweight, robust, and high sensitivity multiplexing capability to the from sensing network, remote sensing capability, and multifunctional sensing capability, such as strain, pressure, corrosion, and temperature. And yeah, fiber optic is also is optical waveguide. Yeah, it's composed of the three part: the core, the cladding, yeah, and also the coating. So that's mean the light is propagated confined in the core, yeah, and with the total reflection, generally made by glass or by polymer. Yeah, there are different type on the fiber optic. A fiber optic is divided in the two group is single mode and multi mode, and also they divided also from the degradation of of indexes. Yeah, like here is a graded index and the other with step index. The principle of fiber optic sensor, they need a light source, yeah, light source, optical fiber, and also the transducer as measurement, and the detector to convert, yeah, from optic to electric. Yeah, that's mean the light source is we have light source, the light, and to cruise through the transducer, and we can measure everything that we need. For example, we detected CO2, we detected hydrogen, for example, and the last optical detector, the processing of electronic. Yeah. Based on the type fiber, there are two. We can see the intrinsic fiber optic sensor and extrinsic and intrinsic. The extrinsic normally we can use external modulator for the characterizes or for the biosensing on medical sensing, and somehow we need also the intrinsic fiber optic sensor. We use the characteristic of intrinsic from fiber optic sensor here. Yeah. So to develop fiber optic, there are three types. Yeah, with the intensity base and also with the phase optical sensor. Yeah, with frequency optical sensor modulated and phase modulated sensor. Yeah, that's depend on what we use to the sensor. Yeah. Also, we can see here from the precision medicine, yeah, is approach to diseases diagnosis, treatment, and preventions, yeah, to seek the maximize effectiveness by talking into individual variability in the clinical presentation, history, genes, yeah, environment, and auto lifestyle. That precision medicine seek to redefine our understanding to diseases onset and progression, treatment response, and health outcomes through the more precise measurement. So the behavior of factor and contribute to the health and diseases. This understanding will lead to more accurate diagnosis, more rational diseases, prevention strategy, better treatment, and also selection. Yeah, the precision medicine require a multi-prognosis approach, requiring technology support in combination area for data management and information technology, computational and analytics tool and system, sensing technology, photonic and biological validation system. The integration precision medicine will integrate the component K, yeah, bioinformatics, system medicine, in silicon modeling, sensing electronic, embedded system, medical imaging, and bio signal analysis, health system, micro and nano biotechnology. Next is I would like to the application of the self-mission interferometer is based on the feedback of generated by light emitting, yeah, the principle self-mixing interferometer is the laser and detector is integrated in one chip, so that that can be used as a sensor. In the self-mixing interferometer, from, for example, like here, was very promising in the future. It is sufficient to detect the emitted power to observe the amplitude interferometer signal here. From, for example, if I have a laser from here and back reflected, and there are Fabry-Pérot interferometer here, and we can detect it. For example, here the sum of the blood pulsation waveform measured on the finger, to with the two-channel analog, self-mixing interferometer like ECG. So we can see here the signal is quite good, comparing with the ECG in electric. But however, here is one of the, I already mentioned before, is laser vibrometer. We can as a sensor from the vibration in the application in biology and also in the medicine. There are with lithium niobate is a substrate. So we can see here the TFV laser with 15-16 nanometer as light source, and we can use polarization splitter here to adjust the polarized light came to into the heterodyne interferometer that can use detected of vibration object. So we can detect is a function of frequency. Here is with the Bessel function we can use that. What is the frequency of the object, for example, here, and also the head rate monitoring based on single mode, multi mode fiber. We can see here like this, and very important is in oncology application and development. We can use Raman spectroscopy, to analyze this for the skin cancer, lung cancer, breast cancer, and etc. So the principle of Raman spectroscopy is Raman scattering by using a laser source, for example, here with the laser diode with 785 nanometer. And also the important thing in is photodynamic therapy. It's using light for photosynthesizer. We can the photosynthesizer is absorbed in. We need photosynthesizer material to kill the tumor cell or the bacteria in the bodies. And now this we can develop micro light source for photodynamic therapy from special purpose. For example, here like from the cancer in the pancreas. This is small micro light source that we need. And here is one example in Dento, the role of photosynthesis antimicrobial photodynamic with Dento laser. So for example, here some child have a problem with biofilm in his teeth, so they can with photodynamic therapy is healing. It's very good. And the conclusion of my topic today is photonic integrated circuit have been developed to replace electrical integrated circuit or conventional optical signal processing system composed of relatively large discrete elements. Fiber optic sensors are excellent candidate for monitoring environment change, medical, and biophysics. They offer many advantages over conventional electronic sensor. And the photodynamic application include a variety of fleet and clinical indication. One of the driving and challenging force in the close interaction and evolvement of almost all known disciplines, starting from chemistry, physics, biology, pharmacy, light, technology, and lesson. to almost a clinical oncology and non-oncological fields. Okay, this is the reference that you can see. And yeah, thank you for your kind attention. Terima kasih dan selamat sore.
Selamat sore, terima kasih. Thank you very much, Pak Agus Rubianto. You have very advanced talk this afternoon. You have talking about essential and basic of light and laser, how fiber optic work, and so many technology approach how to develop the laser. Inside also mentioned about optical waveguide, complete design, especially for medical basic and biophysics. Again, thank you very much for your thought. A big applause for Pak Agus Rubianto. Okay, ladies and gentlemen, right now we go to the question. If you have a question, please you can raise your hand by a reaction in your Zoom application, or you also can write the link that committee also write in your chat Zoom. Okay. Not question, no question. Okay, the first one, I got the two question actually to Professor Nadia. Is it possible to develop a new medium that is better than fiber optic in order to transport telecommunication signal even faster? Please.
Okay. Thank you very much, Dr. Nasori. For telecommunication, so the better medium should be wired, okay, because it has better performance in terms of loss and interference, and compared to the different types of wired that we have, wired technologies that we have at the moment, fiber is the best, the one that has the best performance.
Okay.
Whether we can come out with the new technology, I want to quote the Charles Koch. It's the Nobel recipient. Okay. Charles Koch is the Nobel recipient because of his discoveries of single mode fiber. Yeah, because he discovered the very that it's possible to have very low, nearly 0.2 dB per kilometer of single mode fiber, which allows us to use fiber for long distance. Okay? And he got Nobel Prize for that. He said that he cannot think of any better medium than fiber. That's what he said, but we don't know. What will come in the future, so it depends on the researchers in the materials, I think. But that's what he said. That's I quote.
If you mention like that, still have a lot of challenge actually, yeah.
Challenges.
Okay.
Actually, there are a number of discoveries like use of soliton, of the pulse that can maintain its energy after long distance. So, but there are some advancement research going on to improve fiber still. The fiber to improve the light source that is used to transmit our information. So hopefully with the combination of the best fiber and fiber type and also the best light source, we can have a very good communication system. But to replace fiber, so far, that's what we thought. So it's the best medium.
Okay. Again, Professor Nadia.
Yeah.
How many years NG-PON3 is predicted to be complete or done?
Okay. From my readings, the NG-PON2 is around 2025. It will be introduced commercially. So NG-PON3 some technologies such as WDM-PON, it has been demonstrated successfully.
Okay.
Basically, you can use it, but the thing is the market need for it.
Oh.
The market, because even GPON, not so many users. Users we still have many customers that have
Oh.
not used GPON.
Mm.
So when we are ready, when we have very, for example, services that use very large bandwidth,
Yeah.
and we are connected to so many devices, and maybe the use of hologram, etc., that use very high bandwidth, then maybe there is a need for example, gigabit per second.
Okay. Okay.
But at the moment, we use like megabit per second, not up to gigabit, terabit per user. So there should be also what you call demand from the customer segment.
So okay. I think it's very clear about that. Yeah. Next question. I invite you guys to make a question for both of speaker today, Professor Agus Rubianto and Professor Nadia. Professor Agus Rubianto, we have one question to Prof. Agus. One of the barrier of nanoelectrical integrated circuit is electron quantum tunneling. Is there any problem similar to that for photonic integrated circuit? Like a physical barrier that prevent us to scale down photonic integrated circuit to theoretically just a few atom wide?
Yeah, it's good question. It's not so easy to answer because normally to understand how to develop integrated circuits, we should know very clearly about the properties of substrate, and also for example, for the quantum theories, for example, the teleportation, for example, we need is really stable light source, and also the polarization of light should be pay more attention, because if we send, for example, send the photonic without polarization, is very difficult to develop the teleportations.
Yeah, I think it's that I think you're right that it's almost impossible we can create this one in the short time. Yeah. We need a long time to develop because he has so many approach about high technology.
Yeah.
Okay, both of you, maybe you can answer the question also. There are two types of fiber optic. There are two types of fiber optic. Maybe Professor Nadia also can answer this question. They are a single mode and multi-mode.
Yeah.
The ray propagation of single mode is also different than multi-mode. Can I know the difference of application of two type? Maybe Prof. Nadia or Pak Agus can answer this question. Both of them you can also answer this question.
Okay, ladies first.
Okay, so thank you for the question, and also for Agus for the courtesy. I will answer based on my knowledge in the communication field.
Yeah.
So the multi-mode fiber, it has larger core size, around 50 to 100 micrometer compared to single mode, less than 10 micrometer. So the multi-mode fiber is normally for short links, for very small areas, and also for just interconnect. We call it interconnecting between equipments. But single mode fiber is the one that is used for transmitting information. Like for FTTH, where we use kilometers, hundreds of kilometers, tens of kilometers. That one we need to use single mode fiber, because if you have very large core,
Mhm.
then the large core fiber has much higher loss than smaller core. So that's my answer. Hopefully this answers.
Okay, thank you. Pak Agus?
Yeah. Thank you, Prof. Nadia. You answered very clearly, and yeah. For example, I have experiences in my laboratory in Paderborn University. That's I with my friend develop teragigabit per second. Of course, if we need is single mode fiber. Yeah. But however, if we want to build a sensors for the cheaper, it's better we use a multi-mode. Yeah, because it's easy to fabricate it, and also it's cheaper. But however, the reliability to make a sensor is very flexible comparing with the single mode. Single mode fiber, we need a lot of facility, the height facility, the height precision, like in the laboratory from Professor Nadia. That means this is not so very easy to develop sensor in single mode fiber.
Okay.
Yeah. And normally it's multi-mode is fabricated by polymer. Yeah, it's very easy to develop. And I think it's my answer.
I think it's like a depend of the application. For example, if you we will use like a sensor, some medical sensor or biosensing, maybe we can use multi-mode. But for communication, I think it's better we just use
Single mode, yes.
Yeah, I think it's depend of the application, something like that. Agree about that?
Yeah, of course. But I agree.
Again, Prof. Agus, one question. A photonic integrated circuit is very difficult and high cost fabricated.
Yes.
How we implement this technology in industrial scale,
Yeah.
lowering the cost production?
Yeah. Of course, the cost production is until now is costly. Yeah, but however, if we see that, for example, in the pandemic era, we need a lot of UV. So that means if we can calculate it, how to fabricate it, UV LED or UV lasers can use for healing or sterilization. I think now the price of UV and LED from sterilization is more cheaper than before. That means that's depend on demand. Yeah, if demand need a lot of, so we can fabricated photonic devices is more economist than before. As I was a student, it's very expensive, but nowadays the demand of of UV and LED is very very much in the market. So now it's maybe the fabricate or the from UV, LED, UV, and now it's smiling now today. But as I was a student, it's very difficult to sell the LED or the laser or UV.
Prof. Nadia, one question. How percentage the losses for the fiber application for your application? How many losses?
Okay. So for single mode fiber, loss is around 0.2 dB per kilometer.
Yeah.
So
In how long?
Yeah.
In how long?
okay, the length will depend on the coverage of our network.
Okay.
Okay, but if we experience quite high power loss, okay, we can use optical amplifiers.
Okay.
So this we have inline. It's called inline optical amplifiers. Along the link. Okay, along the link. For example, we have maybe hundreds of kilometers fiber, then we can have this optical amplifier at every 80 kilometers.
Yeah.
Yeah, so this will compensate for the loss. So that's now normally how it's designed. Loss does not stop because we can amplify it.
Oh.
Yeah. But unless if it's too long, very long, thousands of kilometer distance, we need to use regenerator. So regenerator, we have to, it's not, it has more functions than optical amplifier. So we need to convert from optic to electronic. And then we reshape, we have a very clean, nice signals, then we transmit again.
Okay.
But yeah, so that's loss, but it's typically around 0.2 dB per kilometer. Yeah.
The less higher the less lower percentage, yeah, here right now.
The lower, so far what we can, the new optical fiber is around that range. 0.2 is very low.
Very low. Okay.
Because nearly zero.
Okay.
But what advanced fiber does is that this 0.2 dB is at a specific wavelength.
Okay.
13 in optic we call it wavelength, right? 1310 around 1300 nanometer. We have we call it dry fiber. So what they do is they design so that the attenuation for the fiber wavelength is quite broad. You know?
Okay.
So we have low loss region for much larger wavelengths.
Well, again, guys, participant, you have a question, please? No? And if not, also I can push you to make a question. So, Pak Astria, please, Pak Astria, open mic.
Thank you for the opportunity, Dr. Nasori.
Yeah.
Prof. Agus Rubianto. So my question is for Professor Agus Rubianto. About the photonics IC, you mentioned about the fabrication and it can be high cost. I'm just wondering, does ITS or Indonesian institution have the capabilities of this fabrication? And also, if we don't do the fabrication, we still need to perform simulations as well. My background is in electronics. I have no idea on how to simulate photonics and electronics in the same simulation software. So can you give some comments on that? Thank you.
Okay, thank you, Pak Irwansyah. Yeah, of course. Until now, of course, how to fabricate photonic integrated circuit, we need is a clean room. Actually, we need is clean room, and also, of course, is costly. That's depend on the government and also from the private sector. In the private sector, for example, we have a lot of natural resources like silicon and also titanium. We have, but if the government or the private sector want to develop this one, we can solve it. Yeah, of course. Until now, is Frankie say in my group, I also use is simulation, Pak. It's photonic devices like polarization splitter and also for the waveguide, and also we can limited, we can do it. But how to fabricate it? That's need high investment here. For example, if I study in Paderborn University, they have Paderborn is the center of optoelectronic in the North Rhine-Westphalia state, and also we are normally work together with 20 university. But however, in the private sector should be support to develop the photonic integrated circuits industry. Like in 20 university is supported by Philips. And also in Paderborn, somehow we work together with Pirali Photonics in Italy, and also with Alcatel, yeah, from France, and etc. etc. So that mean, yeah, for the simulation we can do it, but we have a lot of simulation concerning a photonic integrated circuit.
It's just a library scale.
Library scale, but however, how to fabricate it, it's need more infrastructure.
Okay.
Okay, thank you very much, Prof.
Thank you, Pak Riz. Again, another question, please. We have still time. We have a time. Sorry. Maybe one question again. No. Okay. Okay. Again, we would like to thank the speaker. If not question again, we would like to thank the speaker who has delivered the presentation in extraordinary way. Thank you very much, and applause again for both of our presenters this afternoon. Ladies and gentlemen, that was the discussion at the international seminar which discussed a passive optical network and its recent development and photonic and fiber for their use in medical physics and biophysics. Furthermore, before we close the session, I will try to conclude the entire seminar this time. The first presenter was about the passive optical network and its recent development. The conclusion of the present are how to develop well and how to improve speed, split ratio from PON, EPON, TPON, etc. With explanation about the generation, of course, and still have a challenge about that. How modulation work with several candidates. And in the second presenter, which about photonic and fiber their use in medical physics and biophysics, the conclusion of the point are essential basic light of laser, how fiber optic work, and so many technology approach how to develop laser inside. Also mentioned about optical waveguide complete design optic, especially for medical and biophysics. Before we close this time, we would like to thank the presenter providing a lot of information to all of us, and we also thanks to audience for their participation of the discussion. Even after this discussion, this time is spaced. Finally, I Nasori as a moderator, thank you very much for coming, and selamat berbuka puasa menanti berbuka puasa. Masih ada beberapa waktu lagi.
Minute. Oh.
We still
Lagi berapa menit?
Yes.
26 lah.
Oh.
Bentar lagi.
Subsequent discussion in another occasion. Thank you very much. Back to MC. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi
Waalaikumsalam.
Yes, thank you very much, Dr. Nasari, for conducting this amazing session. And also thank you very much to our speakers for their excellent lecture today. Please give applause to our speakers and moderator by using the Zoom reaction feature. Furthermore, we would like to present a certificate awarding to our speakers and moderator today. First, this is the certificate presented for Professor Agus Rubianto. I'm sorry, Associate Professor Nadiatul Huda Zulkifli.
Thank you very much.
Yes, thank you very much, Professor. And next is the certificate for Professor Agus Rubianto. Thank you very much, Professor. And last but not least is the certificate for our moderator, Dr. Nasori.
Thank you. Thank you.
Once again, thank you very much to Professor Nadia, Professor Agus Rubianto, and Dr. Nasori for your availability on today's guest lecture series. We believe that your lecture will be useful for all of the participants. Now, before we end our lecture today, we invite you all participants, as well as the honorable speakers and moderator, to take a group photo. To all participants, please open your camera so that we can start our group photo session. Shall we wait for a few moments until all the participants open their camera? Okay, since we have a couple of slides, so please wait for a moment and keep your smile until we finish our photo session. And now I will count to 3. 1, 2, 3. Okay, another one. 1, 2, 3. Okay, thank you very much. We have finished our group photo, and then for the participants, please fill the feedback form through the link bit.ly/feedbackgls that you can also see on the Zoom chat room. And the deadline for filling the feedback form is 1 hour after we finish this session. And we want to remind you that the participant who will get the stamp for it and e-certificate is the participants who come on time, join this event until the end, and also fill the feedback form. Finally, we have reached the end of today's guest lecture series, and we sincerely apologize for any mistakes we may have made in presenting as Master of Ceremony and Committee. Thank you very much to our honorable speakers, moderator, and all participants for the attention and cooperation. We will see you in the next guest lecture series on SDGs.
Assalamualaikum. Thank you very much for having me.
Yes.
Assalamualaikum, Prof. Assalamualaikum, Dr. Nasari.
Thank you.
Dr. Samara, the MC.
So we
And
will
also to all audiences.
to inform you that our next session is on Tuesday, 25th of May, 2021. So we will have no session in the next 2 weeks due to the Eid al-Fitri. So see you on 25th of May. And good afternoon. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam
warahmatullahi wabarakatuh.
Terima kasih Mbak Tamara. Bagus
Terima
sekali.
kasih Bapak.
Terima kasih semua.
Ya,
Terima kasih, Prof.
Terima
Agus.
kasih.
Terima kasih, Prof. Nadia.
Selamat Hari Raya in advance.
Oh ya, ya.
Saya iftar.
Sama-sama.
Buka puasa lambat lagi, 1 jam lebih lagi.
Oh, 1 jam lagi di sana ya kami.
1 jam lebih. Oke.
Kami kurang 26 menit.
Oh, oke. Alright. Tak apa, paling boleh pergi berbuka terus.
Iya, lebih dulu berbuka.
Semua di rumah ke di kantor ya?
Ini di rumah ini, di rumah.
Oh, oke. Sama lah saya.
Sama. Ini kita ini kerjanya itu work from home.
Yalah. Terima kasih banyak Prof. Jumpa lagi Dr. Nasari, jumpa lagi ya.
Jumpa lagi nanti.
Thank you.
Bila datang UTM kalau dah tak ada COVID.
Ya, kalau ke UTM nanti saya tak mampir itu nanti.
Ya, oke.
Makan nasi lemak di sana.
Insyaallah.
Thank you so much, Profesor Nadia Tuhuda, and also
Terima kasih.
Professor Agus, Bapak Nasori, and also Pak Irfan for this section, and allow me, and thank you so much for the participant who coming for this section. And don't forget to fill the feedback at bit.ly/feedback GLS. I would let me end the session in 3, 2, 1, and have a great day, everyone, and see you on the next session in 25 of May. Thank you very much, and see you.
Bye.